Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, count of integers. The problem is a bit easier for the one who know about digit DP, but otherwise for others it is a bit harder. In this particular video, I would be giving you a intuitive, simple approach to solve these kind of problems involving digits or so-called digit DP. And I'm very sure if you watch the video till the end, you will be able to solve these kind of problems by yourself from the next time. I would attach some of the other practice problems of similar kind in the description down below. So after you watch this video, make sure to check them out to strengthen your understanding about digit DP, or in general, it's simple DP as well. So with that, let's get started. The problem states that you are given two strings, nums1 and nums2, and two integers, maxsum and minsum. You denote an integer x to be good if x satisfies these two conditions. The x should be in between nums1 and nums2, and digit sum of x should be in between minsum and maxsum. Now you need to return the number of good integers, and since the answer could be very large, you have to return it modulo 10 to the power 9 plus 7. Now let's take an example. Let's say num1 is 1, num2 is 12, min sum is 1, and min sum is 8. Like they have just misprinted it. So min sum is 1 and max sum is 8. So you have to figure out all the good integers which satisfies the conditions with these four variables. Now the x should lie between 1 and 12. So let's take 1 for example. So 1 already satisfies this, like 1 lies between 1 and 12. Now digit sum of 1 is 1 by itself. So it means, and 1 lies between 1 and 8. So 1 is a good integer, right? Similarly 2, 3, 4, 5, 6, 7, 8 all are good integers because they, like, their digit sum lies between 1 and 8. Now let's take 9. 9 satisfies this criteria, like 9 lies between 1 and 12, but 9 doesn't, the digit sum of 9 is 9, which is not in between 1 and 8, and hence 9 is not a good integer. And similarly 10, 11, 12 are also good integers. So in among these 12 integers, only 9 is not a good integer, and hence remaining 11 are good integers. So the answer here is 11. So hope the problem statement is clear. Now before solving this problem itself, let's try to solve a reduced version of the problem. So in this particular problem, we have these four variables, right? So let's reduce the variable to 2 first. So let's say we need to figure out all the integers less than a given number n, right? Which have digit sum equals to s, right? So notice that the problem asks that the given number should be in between n1 and n2, and digit sum should be in between s1 and s2. But here what we are saying is the number should be less than or equals to, let's say, n, and the digit sum should be equals to s, right? So in this particular example, the value of n is 7524. So we have to find out every possible integer which is less than equals to 7524, which have digit sum equals to 9. Now let's start with the brute force. What is the brute force solution? Brute force solution would be try out every number between 1 and 7524, figure out the digit sum and see if the digit sum is equals to 9 or not. If it is, increment your result, otherwise don't increment, right? Now what is the time complexity of this particular solution? Time complexity would be you are iterating over everything between 1 and this particular number. Let's say this number has d number of digits. So in other words, you are iterating over everything between 1 and 10 to the power d, right? And for each number you are trying to find digit sum. So to find digit sum, you have to iterate over all the digits. In other words, like you have to iterate over d number of digits. So this is the overall time complexity of this particular approach. Now what is the maximum d for which this complexity would suffice? Answer is 7. For 7 you can have this complexity and it will be within the usual time constraint. But in the given problem, it is like 22, which is much more than 7. So we have to optimize this for sure. Now, how to optimize this? So optimizing this is not very straightforward. So let's just modify or reduce the problem even a bit further. Let's say this number itself is not there, right? So let's just forget about this number for a while, and we need to simply figure out how many numbers are there which have digit sum equals to 9. So basically we have this four spaces, right, which we can put one digit. So basically everything here lies between 0 and 9, right? So we have to put one digit in between 0 and 9 in each of these spaces, and then we'll figure out what will be the sum. And if sum is equals to 9, that is a valid candidate. We have to figure out how many good integers are there. So I would strongly encourage you to pause the video right away and try to solve this reduced version of the problem by yourself, because we have solved these kind of problems various time in the channel, right? So hope you have thought about it. So we know we have to put anything between 0 and 9, and we can put anything between 0 and 9 in this particular box. So let's say you put 2 here, right? If you put 2 here, what you can say that, okay, I have put 2 here. Now let me forget about this. Let's say I will just say, okay, how many ways are there in which I can fill these three spaces such that the digit sum of them would be 7. Isn't this problem exactly similar to the original problem? Original problem was, give me the number of ways to fill these boxes such that digit sum is 9. Now we are saying that, uh, give me the number of boxes in which digit sum would be 7. Sorry, give me number of ways in which digit sum would be 7. So hope you can see the recursion here. What we can do, we can simply try out every possible combination here, right? Now for each of this combination, we'll get some remaining digit sum. Let's say you put 2 here, so you will get the remaining digit sum to be 7. So you'll say, okay, find me the number of ways in which I can get the digit sum of 7 with these three spaces. Then you will say, okay, I can put 3 here as well. So find me the number of ways in which I can get 6 as the digit sum, and so on and so forth. So you will try every possible combination and figure out the number of ways for the remaining boxes to be filled with remaining sum. And finally, you will sum them all up and you will get your final result, right? So let's look at the pseudocode. The pseudocode would look something like this. The pseudocode is simple. Uh, we have two variables to our function, index and sum left. Index denote the first index after which we need to fill the boxes, right? So in this particular example, let's say you have filled this, so index would be this, right? And sum left denote what is the sum that is left to be formed. So in this particular case, if you fill 3 here, index would be 1 and sum left would be 6, right? So this will give you number of ways in which you can fill this uh, remaining boxes after index with this particular sum. Now if sum left is 0, like these are the base conditions. If sum left is 0, it means less than 0, it means you have to fill some boxes with sum left less than 0, and that is not possible at all, right? So you will just return 0. In other words, there you are saying that there is no way at all in which you can fill some boxes which have sum left less than 0. If you reach the end, basically you have filled all the boxes. In that case, you can't fill anything else. So you are just checking whether the sum left is equals to 0 or not. If it is not equals to 0, there is no way at all, because you can't fill anything else, right? So that's what we are doing. After that, if it's not the base case, we will do the following. Basically, we will just try out every possible value of a particular index and will get the number of ways to fill the remaining boxes using the same function, right? So in this particular example, let's say this is I, so or this is index. So we will say that, okay, uh, we will fill index with everything between 0 and 9 one by one. For each of this combination, I will figure out how many ways are there in which I can fill the remaining index plus 1 remaining boxes after index plus 1 with this particular sum, right? And you will just sum them all up to get your final result, right? So hope this entire solution makes sense. What is the time complexity? uh, Note, like, first of all, we need to memorize this as well. Basically, we need to just put everything in the cache, and we'll first check the cache. If we have calculated this particular state before, we will serve the result from the cache. Otherwise, we will compute the value using this particular algorithm, right? Now, let's say how many unique ways are there in which you can call this function. Number of unique ways, number of unique values of index would be d, number of digits, right? And the number of unique values of sum left would be s, because maximum value would be s itself. So this is the number of unique ways in which you can call this particular function. And inside this, what you are doing is you are doing some constant time operation, or in other words, you are doing a iteration for which runs over 10 times. So you are doing some constant order c operation, which is where c is equals to 10. So this is the overall time complexity of this particular algorithm. Now, this is much better than the original 10 to the power d into d complexity, because that was the exponential complexity and this is a polynomial complexity, and hence it can work for for constraint greater than 7 as well. Now, even though it works, but this is not the problem that we wanted to solve. We wanted to solve the problem wherein we have to find the number of good integers which is less than equals to the given number, right? So how to solve this particular thing now? Again, this would be very similar to how we have solved this original problem wherein we have filled everything without any constraint. Only thing that comes with this is initially we were able to fill this with 0 to 9. Now we can fill this with 0 to 7. Now why? I would encourage you to pause the video and try to think of this, of why this is the case by yourself. So the thing is, you already have said that you will be having 4 digits, uh, and if the actual number is not 4 digit, you will pad this with 0. For example, let's say you have to write 12, you will say it is 0012, right? Now we are comparing two 4 digit number, and we just wanted to see which one is greater. Now, how to compare two equal digit number? The simplest way is to just start from the greatest digit and see the first non-matching digit, right? Let's say this is the first non-matching digit. Let's say this is 5, this is 7, this is 5, and this is 1. So this is the first non-matching digit. So whichever is smaller in that first non-matching digit will be the smaller integer, right? Why? The question, the answer is simple, because you know everything after this will not matter if it already is smaller here. So basically we are saying that we put 2 here and we can put some number here. Now we put 1 here and we can put some number here. So if even if you put 9, the greatest value here, this would still be less than this, because you already have 2 here and the smallest value that is possible with 2 is 20. So even the smallest value here is greater than the largest value here, and hence we can say simply that the first integer which will be a mismatch, that will be the deciding factor of which integer would be the greater integer, right? So that's where, instead of filling this, like we will never fill this with 8, because if we fill this with 8, we know that this number would anyway be greater than this particular number, and that's what we don't want. So that's why we will only fill the first index with everything between 0 and 7, right? What is the difference? Difference is, initially we have filled it with everything between 0 and 9, but now we are saying that we'll fill it everything between 0 and 7, right? Now let's say you put anything between 0 and 7. Let's say you put 6 here, right? If you put 6 here, this number is already smaller, right? So basically you are saying that this is the first non-matching digit and this number is already smaller. Because this number is already smaller, now it doesn't matter what you put here, right? So you can again, is free to put anything between 0 and 9 in each of these boxes, right? Now if you say that, okay, this is not matching, in other words, you will say, okay, let's say this is 7 itself. So this is the prefix, this is not the first digit, which is different. So in that case, you are again forced to put everything between 0 and 5 only, right? So let's say again you put a smaller integer here. In that case, this is the first non-matching digit, and because this is the first non-matching digit and this value is smaller, you are free to put anything after that. But in if you have put a 5 here, then again you are saying that this is not the first non-matching digit, and non-matching digit would come afterwards. So in that case again you are forced to put 0 to 2. So what's happening? Let's look at it. If like what to put here depends on two things. What is the value here, right? And second thing is whether this is the first non-matching integer or not, or whether there is an integer before this which is already non-matching, right? So let's say there is an integer before this which is non-matching, right? So if there is an integer which is non-matching and we are already sure that we should be having a smaller integer here, so we can say simply that if there is an integer which is non-matching, we are free to put anything here, or we can try anything between 0 and 9. But if there is no non-matching digit before, in that case we have to put everything between 0 and 2, right? So what what state we need to carry forward to figure out what all we can fill here? The answer is just a Boolean variable, whether there is a non-matching digit or not. If the Boolean variable is true, it means there is a non-matching digit. Then you can fill it with 0 and anything between 0 and 9. If that Boolean variable is false, it means there is no non-matching digit. In that case, everything is similar, and hence you need to put everything between 0 and 2, right? So that's the simple change that will happen, and you can just apply the exact same algorithm with just one more state which says whether there is a non-matching digit before or not. So let's see how the pseudocode would change. We just have added one more Boolean variable which is already smaller, or in other words, like whether there is a non-matching digit before or not. Now these base cases are exactly similar, right? The only thing that changed here is we need to figure out whether like what all we can put here. Previously we are simply putting everything between 0 and 9, but now if there is already a non-matching digit, then we are free to put everything between 0 and 9, right? If there is no non-matching digit at all, then as we have discussed, we have to put everything between 0 and current value, and current value let's denote it by s of index, right? Now once you figure out what all you can put here, you can simply iterate over it, and then for the next case what you will do, you will again figure out whether there is a non-matching digit or not. So if there is already a non-matching digit before, in that case you can simply put the new value as true as well, because this just means that this just needs to be true only when any one of non-matching digits are there before. So this says that before index itself there is a non-matching digit, so in that case you will put uh, true because there is a non-matching digit before index plus 1 as well. But if there is no non-matching digit before, then the value of this boolean depends on what we are putting at the current place. So if we are putting s of index, then there is no non-matching digit as well. But if we are not putting s of index, it means there is a non-matching digit. So basically this would be not equals to, sorry for that. So if there is no non-matching digit at all, we need to put true, we need to put false, otherwise we need to put true. So if it is already true, it means we can simply put it true. If it is not true, then we know that we can only put everything between 0 and 2. So if we put 2 here, then only the variable will be false. For all other value, that is 0 or 1, the variable would be true, because this would be the index which would be the first non-matching index, right? So that's what we are doing. If the value of I is not the end, or whatever we are putting at the current index is not the value in the original place, in that case we'll put will use false as the non-matching, otherwise we'll use true, right? So this is the entire algorithm that will solve the given question as well, the given reduced question. And what is the complexity here? Nothing changes at all, right? We are just doing the exact same thing. Only thing that changes, there is a extra state in our function, recursive function. Now, because in extra state, we need to figure like number of unique ways to call this function will change. Initially, it was order d into s, right? Now it will be order d because of this index, right? Into s, the number, the maximum sum possible, right? Into 2, because this is just a boolean variable and it can have only two value, either true or false. So these are the number of states, and again within each state what you are doing is, you are doing a for loop over maximum of 10 times. So this is again a constant factor which we are taking in. So overall the complexity doesn't change much. So you can say that the complexity is still order d into s in some sense, right? So what we have just done is we have solved the reduced problem completely. The reduced problem was count the number of integers which are smaller than a given number n and which has digit sum equals to s, right? Initially, the brute force for that particular solution was order 10 to the power d into d, and we have reduced this to order d into s. Like there are some constant factor as well, but we are kind of ignoring that for now. So we have reduced this to order d into s. Now this can work for uh, like d equals to 1000 as well, because maximum sum when d is 1000 and 9000. So this will also work for d equal to 1000 as well. And in the given constraint, d is just 22. So this will surely work. Now, uh, original problem was not this. Original problem had two more things. Original problem states that you need to figure out the digit sum should be in between sum s1 and s2. Like we what we have solved is digit sum equals to a given variable, but now we have to figure out digit sum is in between two variables, right? So let's just try to modify this initial algorithm itself. So initially we had something like this, right? For the very reduced problem, we can simply rewrite this particular algorithm as this. So instead of subtracting things from here, we'll keep on accumulating sum, right? And whenever we reach the last index, we can just check whether the current sum is equal to the given sum. If it is, we return 1, otherwise we return 0, right? They are exactly the same algorithm, but this will give you the power that you need to figure out whether the digit sum lies between given range or not. So instead of equals to sum here, you can simply say whether the current sum lies between sum s1 and s2, right? And based on that, you will return 1, otherwise you will return 0, right? So that's the only change that you need to do to also notice that the complexity doesn't change. It's just that we have rewrote the function in a bit different way. So the overall like complexity is still same, and we are now able to answer the question that given a number n, figure out how many numbers are there which are less than equals to n, and the digit sum lies between s1 and s2, right? So this is something now we have figured out. But original problem also states that the given number should be in between n1 and n2, right? So how to solve this particular part? So I would strongly encourage you to pause it right away and try to think of this last piece or last variable of the problem by yourself. Hope you thought about it. A simple hint could be a prefix sum. So let's say you already know how many integers are there, or how many good integers are there which are less than equals to n1. you can simply figure out how many good integers are there which are less than equals to n2, and you can subtract them to figure out how many good integers are there which lies between n1 and n2, right? So just the standard prefixum thing, we figure out everything that is less than n1, we figure out everything that is less than n2, and then we subtract both of them to figure out everything that lies between n1 and n2. And that's it. That's the overall complexity. Basically, we are doing this particular algorithm two times, one for n1 and second for n2. And that doesn't change the time complexity much. And the given problem, we will be able to solve this in order d into s time. Now, if you have watched till this point, I would strongly encourage you to pause the video and try to get this particular solution submitted in Leetcode, because we have looked at the pseudocode already, and this is the only pseudocode that we need to call twice, one for n1, one for n2, and we'll just subtract them. So, hope you have at least tried solving this particular problem by yourself. Let's look at the code finally. So as we have discussed, like this is like we have put maximum and min sum in some global variable. So that's what we are assigning here. And finally, we'll just figure out how many good integers are there that are less than num2. We'll figure out how many good integers are there that are less than num1 minus 1, because there is equals to here as well. So we need to consider num1 as well. So we just figure out how many good integers are there which are less than num1 minus 1, and then we subtract both of them, and that is the answer. So we just do plus mod because we need to give everything modulus, and subtraction might yield a negative result. So this is just the standard modulus stuff. Now let's look at subtract one first, because this is the simplest one here. So how to subtract one from a given number? So notice that this number is not a integer or a long integer. Instead, it's just a string, and you can't actually represent this in an integer as well, because integer can only store, or long, the largest integer possible is 64-bit, and that can only store somewhere around 10 to the power 18 or 10 to the power 19. So you can't actually store 10 to the power 22 in an integer as well. So you have to subtract one from a given string itself. Now how to subtract one? Let's say the given string is 200 or 5200, and you have to subtract one. So it's the basic math that we do in like 4 or 5 class. Like you will just see, okay, what is the first non-zero number, right? So you will just subtract one from here and make everything 9 afterwards, right? So that's the simplest thing we are doing. We will just figure out the first non-zero index. Once we figure out the first non-zero index, we'll just subtract this value, and we'll just do everything after that to 9. Now notice that we will find out first non-zero index for sure, because num1 is like every number is greater than equals to 1. So there should be at least one non-zero index for sure, right? Now after that, we just figure out the good integer less than x. So let's look at that. So we have this DP, which is nothing but the cache. Like remember, we don't need to recalculate every state here again and again. So that's where we will maintain the cache. So this cache has three things: this boolean variable which takes only two value, this index which can take only 23 values because the maximum number possible is 22, and the sum left which can take only 200 because the maximum sum possible will be 23 into 9. Basically every digit is 9. That is the maximum sum possible. So you'll just do that, and this is something you will end up with. So what we are doing here, we are just initializing everything with -1, right? After that we build s. Now what we are building here is uh, we are building this particular string. Now notice that we have like we this entire algorithm works because we converted the every number to a 4-digit number, or in other words, every number to a d-digit number, where d is the size of the original number. So in this particular example, because the maximum number can be of length 23, I am just converting everything to a 23-digit number. So n is 23, and what we are saying is if the length is not 23, I will just pad it with zeros and then have this particular x. After that, this is the recursion that we were talking about. It has three variables or three states. First is smaller, or in other words, whether this is the whether there is a non-matching digit before me or not. And second is the index, and third is the sum. So let's look at it quickly. If the index is the last index, we'll just check whether the sum that we have accumulated, whether it lies between the given min sum and max sum or not. If it is, we'll return 1, otherwise we'll return 0. Otherwise, we'll just check our cache if this particular, like initially we have we have initialized everything with -1. So we'll just check if it is not -1, it means it is something that we have already calculated. So we'll return that. Otherwise, we will try to calculate everything. Um, we'll try to calculate the value of this particular state. How to do that? As we have discussed, we'll start. We can put every. We'll try every possible value that we can put at the current index. So we will try with 0 to 9. Now, if there is no matching index before, it means you can't put anything between 0 and 9. Instead, you are forced to put everything in between 0 and s of I, or s of index. So we'll iterate over everything between start and end, and we will call the same function with uh, index plus 1 and sum plus I, and a value for is smaller as well, right? So we already have discussed how this is smaller is calculated for the new, like for the next state. So I'm not discussing this again. Finally, we'll just sum them all up to get the answer, right? So there is a small thing here, like I haven't put modulus mod here, and even without this, the solution works. So it means the test cases are weak. So, but if you just code it, there are enough test cases that would catch you any error that you have done in this particular algorithm. So that's it. Hope you now understand how do digit DP. Like this entire thing is called digit DP. Like there's nothing fancy I have seen. It's just that one more state got added, and that state just denotes whether there is already non-matching index or not. So every digit problem boils down to exact same problem. So what you can just like you can just try to convert everything to the largest digit possible. So basically, you want comparison to be as simple as possible. So we can't compare a three-digit number with four-digit number very easily. So that's where we have converted everything to a four-digit number itself, and then we figured out what is the first non-matching index to figure out which number is smaller. And we've because we only need the first non-matching index to be for a number to be smaller, that is the key state that we will be depending on for anything that we have put before, right? So that's the simple trick that we will do in every digit DP. So as discussed, I will try to put some practice problem of this in the description down below. Make sure to solve them by yourself. If you have any doubts, feel free to post them in the comment section below. I will be able to answer. And if there are enough demand, I can create videos for those follow-up problems as well. So that's about it. Again, one last thing, you can put this entire same algorithm for or this entire same algorithm would work for 10 to the power 100 as well, or 10 to the power 1000 as well. So I think they have just uh, reduced the constraint unknowingly, but this exact same algorithm would have worked for 1000 as well. So that's it. Hope you understand. Hope you like the video. Make sure to like it and do subscribe if you haven't already. And I will see you in the next one. Thank you.